I'm going to write on here, record a video as I go, and then we can post the video and post a PDF later if for anybody who missed it and wants to see it, or if you want to see it again. So this is sort of an intro to the ideas of statics. And then I'll give a little thing about how this will go into calculations that you use in biomechanics. And so before I start, I know probably most of you have seen like torques and moments in classes before, but I just want to give a little reminder of what a moment is. So the mathematical background, or like the physics background for this, is the moment of a force about a point. That's a lot to say, so people usually don't say all that. They just say, they call it a moment or a torque. But it's worth keeping in mind that all of this stuff is important. The moment depends on what you choose to calculate it about. That's the point, and it depends on what the force is. And mathematically, the definition is like this. If you have, so let's say this is just some arbitrary object. And somewhere on this object, let's call this point P, a force is applied. So I'll call this the force F. It's a vector. And somewhere else, it doesn't matter where for this definition, but it has to be chosen. There's some point A. So I'm going to call that the about point. You call it that, Sue? The about point? I think about point. I don't know if I just started saying that or if I'd ever heard that before. And so you can think of the idea of a moment is that if a body has the ability to rotate around a point, so imagine that it's free to rotate around this point. You apply a force here, it'll make this thing rotate. Okay. And the way you do the calculation is you figure out the vector that goes from the about point, from A, to that point P where the force is applied, and we'll call this vector rho, Greek letter rho. And then the moment about A produced by that force is the cross product of rho and F. And the idea of that is, if you think of, so I think this is the easiest way to think about it. If you're trying to turn a stuck bolt with a wrench, and say you're capable of applying 100 newtons of force or something, what's going to happen if you apply that 100 newtons of force here, or here, or here? You know from experience that you're going to have the best luck if you apply that force as far away from what you're trying to turn as possible. So that's why if you're dealing with things that are really tightly stuck, you're going to use those giant monkey wrenches. If you apply it here, it'll be harder to turn. If you apply the force here, you could apply 1,000,000 pounds of force and it's never going to turn. It's just going to rip the bolt apart, So that's the idea that the moment is getting at. That cross product calculation does all of this for you. It determines how much of a tendency to cause rotation that force F is applying. Okay. So now here's the statics that we're going to use. It's going to be 4 sort of facts that we're going to use for bodies that are in equilibrium. So bodies that are not accelerating, not rotating. So no acceleration and no rotation. The first one is Newton's second law. And that says add up all the forces that act on the body, whatever body you're choosing to investigate. Those forces have to add up to be equal to 0. The second thing is sort of, you can think of it as the rotational version of Newton's second law. I think most people call it the moment equation. And in equilibrium, that says no matter what point A you choose as the about point, moments have to add up to 0. So that's for any A. The third thing we're going to use is Newton's third law. And that says for every action, there's an equal and opposite reaction. For us, what that means is if you have a contact force between bodies A and B, the force vector that's applied on A by B is equal and opposite to the force on B by A. And the last fact that we're going to use is in 2 dimensions, a pin joint, you can think of that as like a hinge, can apply 2 components of force to any object that it's attached to. And we'll see how this works. So I'm going to go through sort of a simple, common sort of statics example, and then I'm going to go into a similar mathematical problem, but one where you can see how you would use this to calculate muscle forces, joint forces, the kind of stuff that could be useful in medical cases. All right, so the first example, any questions about, so the 4 things that this is based on, any questions about that? Okay. So here's a pretty typical, statics problem you would have to do. Let's say you have one beam there, one beam here. They make an equilateral triangle. Say that the lengths are, each of these 2 lengths are the same, half a meter. And let's say that the mass of each one is 5 kilograms. It's equilateral, so these angles are all 60. And let's say that there's a force of 1,000 newtons applied to the top. I'm going to call, just for bookkeeping, I'm going to call this member number 1 and this member 2. And we want to find the external loads. What are all the forces acting on member 1 and on member 2? It's going to be the same, there's symmetry in this problem, so it's going to be the same on each one. So what are the forces acting on each beam? And you can imagine if this was an engineering problem that this was part of some kind of machine or something, people would do calculations like this so that they would know what kind of bolts they had to use, what kind of materials to make that pin out of, how thick those beams would have to be. You need to know whether the materials you use are going to be able to support these loads. So first I'm going to draw free body diagrams of the two beams. So beam one, the one on the left, it's like that. And I'm going to, the one thing that can be a little tricky about this is I'm going to assume that, so when you decide what body to isolate, you can isolate a single thing or a collection of things or a part of a thing. You just have to be clear to yourself about what you're including in the chosen body. I'm going to include this pin as part of member one, okay? So that pin is not part of member two. And that means that this 1,000 Newton force is not applied to member two at all, right? It's only applied to the pin, which we're saying is part of member one. So what loads are applied? There's the 1,000 Newton force here. That's arbitrary. I could have said that the pin was part of member two, and then that 1,000 would have appeared on member two instead, and in the end, all the numbers will come out exactly the same. It's kind of cool how it works, but and then there's a contact force between body one and body two. So I'll call this the force on one by two. That's a pin joint. So I said, remember the pin joint applies two components of a force vector to whatever body it's connected to. So that's why that's two components of a force vector. Down here, there's a pin joint. I'll call that the reaction force at A. And then there's a weight force, 5 kilograms times 9.81, that's 49.05. See, what notation do you use for forces? Do you use this kind of notation like F12, F21? 1 on 2, yeah. So, FYI, the world is like split 50-50 into people who call this F12 and people who call it F21. I was shocked to discover that, but it tends to be, unfortunately, like I think engineering people would say the force on 1 by 2 is F12, and physics people would tend to say the force on 1 by 2 is F21, like 2 is applying the force to 1. So be careful of that when you see it. Be sure you know which one people are talking about. And okay, so I'm going to make a little table here just to organize this. For each one of these forces, we're going to calculate our row vector, our force vector, and then take the cross product to get the moment. And that means we have to choose an about point. You can choose any one you want, but I'm going to do it here. It's going to end up simplifying things a little bit. So first I'll deal with that 1,000 Newton force. The row vector to get, so what's the vector from our point A, that red dot, to where the force is applied? It's the same point, so that's a 0 vector. The force is in the negative y direction, so this is 0, negative 1,000. And if you cross 0 with anything, you get 0. So that's like what we have here is like the example of trying to turn a bolt by pressing down right above the bolt. You need some kind of moment arm to get any rotation at all. And then the force on 1 by 2 That's a row vector of 0. Force vector of F, 1, 2x, I'll call it 1, 2y. 0 cross product. Then the weight force, that vector, so now we have to do trigonometry to get that vector, but it turns out it's just going to be negative 0.125, negative 0.217. The force vector is 0, negative 49.05. And if you take that cross product, you get 6.13. And I'll just continue this down here. And the last force is the reaction force down at the ground, that force RA. The vector that goes from the red dot to A is negative 0.25, negative 0.433. The force is RAX, RAY. And if you take that cross product, you get negative 0.25 RAY. So here's how the cross product works. It's this times this minus this times this. And so plus 0.433 RAX. But now the nice thing about having this table set up here is you have a record of all the, so Newton's second law, if it's for something in equilibrium, says add up all the forces, just go straight down this column and set the sum equal to 0. And the moment equation says add up all these moments, set them equal to 0. So you get your first set of equations. Newton's second law says 0, negative 1,000. Well, let's do it in, let me do it as two separate equations. So if you add up all the x components, the first components of these vectors, it says f12x plus rax is equal to 0. Add up all the y equations, I'm sorry, all the y components of these forces gives you the second equation that says negative 1,000 plus f12y minus 49.05 plus ray is equal to 0. And then the third equation comes from the moment equation, says add up all these moments, set those equal to 0. So we have 6.13 minus 0.25 ray plus 0.433 rax equal to 0. Okay, so we got these three equations from the first body. I'm not going to go into so much detail on the second body, but that's where the equations come from. So we have three equations. How many variables do we have? We have f12x, f12y, rax, ray. So three equations, but four variables. Okay, so that's bad. It's not so bad, but you can't solve anything. So the next step is we're going to draw a free body diagram of the other beam. We're going to come up with Newton's laws for the second beam. It's going to give us three more equations, hopefully without introducing so many more variables that we still have more variables than equations. Hopefully the equations will catch up to the variables. And then once you have that, you can solve it in a calculator or by substitution or something. We're going to end up with a system of 6 equations for 6 variables. Anybody have any questions? Yep.
So how did it, what would have been changed or altered if you had chosen a different
Well, it just would have meant that if I would have chosen this as the about point, then I would have had no moment that I had to calculate here. So that would have been made it a little easier. And I would have still had to calculate one here and here and here. So it's just one more calculation I have to do. Just like as far as making it easier or harder. But you would end up with equations that look different. Like your system of equations would look different, but in the end, all the answers would come out the same.
result?
Yeah, it's totally the same.
Okay.
So that's your choice. You can totally do it. If you can identify the point where you have the fewest forces and choose that as the, yeah, it just makes it a little faster. Any other questions? Mm-hmm. What kind of force? So if you were going to try to figure out, like for example, so it can get more complicated in a couple of ways. So you could have instead of having this force applied right here, you could have, forces aren't ever actually applied at a single point. They're spread out over, even if it's spread out over a small distance, they're always spread out some. So you could have this 1,000 newtons spread out over the whole thing, and that would make it a little more complicated. You could, and depending on the way it's distributed, you might have to use calculus. If it has a very simple, like uniform pattern, then you wouldn't have to use calculus, but it would get a little harder. And then I think maybe what you're sort of getting at is, maybe I'm wrong about this, but if you wanted to figure out, say, where this thing was the most likely to break, in order to do that, you'd have to, after you get the answer that we're getting right now, you'd have to go in and figure out what are the internal forces that, like how much is the metal straining here to avoid breaking apart. That's an internal loads calculation, and yeah, you'd have to, again, if depending on the types of loads you have, you might have to use calculus or you might not, but it does get a little more complicated. But all we're trying to do is just figure out what RA is and what that force on 1/2 is. Okay, so I know this is painfully boring, so I'm just going to do a free body diagram of this, give the equations, and we'll be done with it. So free body diagram of body 2. Okay, so what loads are acting on body 2? This is connected to the ground by a pin joint, so there's definitely a force over here. I'll call this RC. And that's 2 components of a force vector because that's what pin joints do. And then there's a weight here of 49.05 newtons. And then up at the top, remember that we decided at the start that the pin itself we were going to treat as part of member 1. So that 1,000 newtons force isn't applied here, it's applied to member 1. So, like you can imagine, this has a hole, and member 1 has a pin-shaped thing that goes through that hole. So the only force up here is the force on member 2 by member 1. It's the force that that pin is applying here. Since that's a pin joint, we know that that's 2 components of a force vector. I'm left-handed, so I have to keep going and like erasing all the little marks my hand makes. Just one more thing that makes it horrible to be left-handed. Okay, so this is the force on 2 by 1. And remember that Newton's third law says the force on 2 by 1 is the opposite of the force on 1 by 2. So I'm going to make that switch here because otherwise this would introduce 1, 2, 3, 4 new variables, and we'd still have more variables than equations. But using Newton's third law, I can make it so we only introduce 2. Yeah, sure. You can do it 2 ways. I do it this way. I do it where these are always showing the, these are just always in the coordinate axis directions. And then I switch the direction with the negative there. But a lot of people, maybe more people, switch the directions of those 2 things, and then they just call it F12. You know, but you can't do both, or you get a double negative and your signs are all backwards. Yes. Okay, so now from that you get equations that say, I'll just write the equations. RCX minus F12X is equal to 0. And RCY minus F12Y is equal to 49.05. And the moment equation comes out to be 0.433 CX plus 0.25 RCY is equal to 6.13. And now we have 6 equations for 6 variables. And you can solve it. And in this case, what you get is, so let me draw the bodies. So here's member 1. We end up with a force vector down here of 302.85, 549.05. Then you have the weight force. And then at the top, you have 2 forces. I'll just add them together. So up here you have a force negative 302.85, negative 500. And then member 2, in C you have negative 302, positive 549, and then you have the weight. And then up here, you have positive 302 and positive 549. That's not right. This is negative. Okay. Negative 500. Negative, that should be, yes, you're right. Yes, that should be negative 500. Yep, thank you. Okay, so then if you wanted to go, you know, if you wanted to figure out where this beam was in danger of breaking, you use these external forces that are acting on each of these beams and go through, you know, point by point figure out where the internal loads are big, and then what you would really do is you calculate those internal loads, and then you go back in with those internal loads and calculate stresses and strains to figure out where it's going to break. That's the kind of stuff that we do in deform. So after you do this sort of statics analysis, then you use that to calculate stresses and strains in deform. Okay, done with that. Any other questions about, so that was just sort of a, kind of a standard statics type problem. But now I want to do an example of that in biomechanics. And I'm going to call this orthopedic biomechanics because biomechanics refers to so many things. You can be talking about pressure in blood vessels or, heart valves or whatever. But I'm just talking about muscle and bone and joint forces. And so I'm going to use the same approach to show that when you stand up on one toe, so just do this. Okay. The tension in your Achilles tendon is a tension of more than twice your body weight. And second, the contact force at your ankle is almost 4 times your body weight. So, I think for most people that seems like a pretty surprising result. Like it's hard to imagine how that could happen. And yes.
So if I were going off a jump,
Mm-hmm.
a snowboard, the force that it would take to break my ankle would have to be 4 times my body weight. Is what you're saying? Is that right?
Yeah. So that's the kind of thing you would use it for. Like you'd measure. So what we're doing here is statics, and so you have to be a little careful when you get really fast moving things because then there's a lot of dynamic forces too that we're not accounting for. For motions where you're not moving too fast, this is a pretty good approximation. Like you could use a statics analysis to figure out forces during walking or something because there's not that much dynamic stuff going on. But if you're talking about like a big jump or something, there's probably a lot of stuff. There's definitely a lot of stuff you're missing with this approach. But you can do this same kind of analysis using dynamics. It's just more complicated, Yeah, right. Okay, so the way we're going to model the body, so what we're talking about is this. Nice legs. I forgot to leave room to make arms. Yeah. Yeah, that's a good trick. Okay, so, and, but he's standing on one leg, so. Okay, so this is basically what we're picturing, this person standing here like this on the 10-meter platform. But what we're really doing is with the center of mass of this thing here. So all we care about is the forces that are happening here. All the details here, that doesn't matter to us. We're just going to treat that all as like mass that's centered over where the toe connects with the ground. That's how it has to be, or it just tips over. It doesn't matter what muscles are firing when. And we're going to assume that the toe is connected to the ground by a pin joint. We're going to assume this is a pin joint at the ankle. And we're going to assume that the Achilles tendon goes from this point at the heel to this point on the leg. And we're just going to treat it like a cable. Okay. And just to make it simpler, I chose that to be vertical. It doesn't really change any, it just makes the math a little more of a nuisance if you have it at an angle. So let's figure out some of the distances. We'll say that this length is 0.25 meters. And we'll say that the distance from the Achilles tendon to the ankle joint horizontally is 5 centimeters, so 0.05 meters. And we'll say that from the heel to the ankle vertically is 2 centimeters. And we'll say that from the ankle joint to the ball of the foot is 12 centimeters, 0.12 meters. And how do you get those measurements? Well, I got those measurements from like looking at my foot and trying to guess how far it was from one thing to another. But for when these studies are important, you get it from like cadavers, actually taking the measurements. You can do it from MRIs, but that's really expensive. These are somewhere in the right ballpark. Yep. 0.02, yeah. Okay, so we're going to do the same thing we did before. We're going to isolate the foot, and I didn't give a mass. I guess I just called the mass M. And I'm going to assume that the mass of the foot is nothing, just again to get a little of the numbers out of it. That doesn't really change anything. The foot doesn't weigh very much compared to the rest of your body. So the mass is M. Okay, so first I'm going to isolate the foot, then I'm going to isolate all the rest of the stuff. Keep stopping me if you have any questions. Okay, so the foot looks something like that. There is a force vector here because it's a pin joint, and I'll call that RT for toes. There's a force vector here that I'll call the force on the foot by the body. And then there's a tension in the cable that's just pulling straight up. I'll call that T. And if you go through the Newton's second law and the moment equation, you get these three equations. R T x component plus the force on the foot by the body x component is equal to 0. That's the x component of Newton's second law. The y component of Newton's second law is RTY plus force on the foot by the body y plus t is equal to 0. And the third equation, this is the moment equation, and you can imagine with the row vectors that you have to calculate, that's when all these dimensions come into it. And so we get negative 0.02 times force on the foot by the body x component minus 0.12 force on the foot by the body y component minus 0.17 t is equal to 0. And variables, we have 1, 2, 3, 4, 5 variables. And then we'll go to the free body diagram of the body. That looks something like this. So here we have the force on the body by the foot. And Newton's third law says that's negative force of the foot by the body. And we have the weight force. That has a magnitude of mg if the mass is m. And then we have the cable force straight down, and that has the magnitude t. And from these, you get this equation that says the component of the force on the foot by the body is equal to 0. The y equation from Newton's second law says negative force on the foot by the body y minus t is equal to mg. And the sixth equation says 0.05 t is equal to 0.12 mg. Okay, so now we have 6 equations for 6 variables. Actually, no, we don't. We have, how many do we have? 5 variables still. Some of those equations end up being redundant, so that's why it still works out. So now equation 6 says, you can see right there that T, equation 6 tells us that T, that's the tension in the Achilles tendon, and also in the 2 muscles that attach the Achilles tendon, is equal to 0.12 mg divided by 0.05, or in other words, 2.4 mg, or the tension in your cable, in your Achilles tendon, is supporting your weight, 1 foot, is supporting your weight by applying a tension that's 2.4 times your body weight between your foot and your leg. And then the x component of the force, that contact force at your ankle, is 0, but the y component of that force, the force on your foot by your body, y component, is equal to negative 3.4 mg. So if you have problems with arthritis or something, you know, that's the kind of thing that you would want to figure out to see, you know, what kind of motions or whatever are going to be bad for the cartilage in your joint. Okay, so this is, so the ankle force is 3.4 times body weight. And intuitively, the way that comes about, maybe you could see it sort of once I drew the Freebody diagram. In order to keep this thing from just tipping over, you know, the muscles and tendons between your heel and your lower leg have to apply pretty big force. And that force, the bigger that force is, the more that tendon is pulling the two bones together. And so your ankle is having to deal with not just the weight that's pushing the two parts of the leg together, but the weight and additionally the fact that that tendon is pulling even harder those two together. And that's, you know, that's where that big factor comes from. Any questions about that? Yes.
So do athletes use this type of research and mathematics and stuff like that, obviously with the other components and other variables that could,
yeah,
my snowboard example again, like would somebody who's trying to do an insane jump do this type of math?
Yes, they do. You know, have you ever heard of the orthopedic surgeon? I don't know if he's as big anymore, but James Andrews, and he's the guy, like, if you watch ESPN and they talk about somebody's having Tommy John surgery or some kind of surgery, it's always by this one orthopedic surgeon or used to be, in Birmingham, Alabama. And he has this big institute where they do this kind of analysis. They'll watch somebody pitch with the little reflective markers all over their arms so they can get a real accurate idea of what the motion is like. And then they'll go in and analyze, like, what are the forces here and there, and is there something that we could do, some minor change to the motion that we could do so that this person isn't going to keep tearing those ligaments. So yeah, it is. They would use dynamics instead of statics, but the idea is the same. Yeah. Yeah.
Spend a lot of time trying to perfect that.
Right.
So I can assume.
Yeah. I mean, I've only heard of people doing it for injuries, but you could imagine that it, you know, to prevent injuries. But you could also imagine that it maybe could be useful for just trying to, like, improve performance, you know. I guess I've heard of sprinters, hurdlers and stuff doing similar analysis to, but mostly I'm just aware of people trying to prevent injuries with that kind of stuff. Any other questions? Yes.
So, like, is this fairly new, essentially, to be applying this to athletics? Like, would somebody like Evel Knievel not have really done much of this? Just kind of like
yeah,
fly up in the air. And
that's right. And the reason that it's fairly new is because you have to use computers to do it instant by instant, sort of, you know. And so this way of thinking about, like, people, it wasn't the analysis that would have been hard 30 years ago, but you couldn't, there wasn't technology, there weren't computers good enough to make it really practical, you know. So I believe it was like in the mid 80s, that's when the first papers that I remember reading about that stuff, putting markers all over and measuring body positions that way, come from like the mid 80s. Yeah, well, that's a great question. Yes, it's very applicable to aesthetic design because if you, I guess two things. Like, first, just the same reason that we would have done that analysis of that structure that I did at first. If you're just trying to make something that is going to be as light as possible without breaking, you need to know what kind of loads are going to act on it over the load cycle. So in that way, it's important if you know that you can use styrofoam here, but here you have to use some kind of strong plastic, or here you have to use metal or whatever. They need it for that. Mm-hmm. Right. Yeah. So that's what I was going to say for the things that actually have dynamic ranges of motion and apply forces and stuff at different points in a motion. You would do this kind of analysis to figure out at different points. I'm thinking of like a lower leg prosthetic or something, but at different points in walking, what forces need to be applied when, and then you can use that to whatever you do. I don't know. Do they have like motors sometimes in them, or but I guess if you're using springs or something, you could figure out, yeah, you know what I mean. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah, it is. It's very interesting. Mm-hmm. Mm-hmm. Any other questions about this? Yes. Yeah.
Would they apply this to building bridges? Because that doesn't, I don't think, have a pin joint that would be like welded together. So
oh yeah, that's a good question. Okay, so yeah, so if you use this kind of approach to do calculations involving bridges, you treat it like there's a pin joint here and a pin joint here and a pin joint here. But when you really see a bridge, it's all the joints look like this, and you know what I mean. And that's not a pin joint, obviously. Like those pin joint rotate around. But yeah, you would do the calculation as if it was a pin joint, because so when you have a pin joint like this, all that thing can apply is forces. It can't apply any moments on its own to keep it from rotating. But the forces here predominate over the moments that this can provide anyways, because if it didn't, things would just flex enough that eventually it would only be providing forces anyways. And so it turns out that this structure, if you build it so it would be stable with pin joints, that's what it's going to act like pin joints anyways.
It's a really strong pin joint.
Yeah,
essentially.
Right.
Okay.
So yes, that is sort of a funny thing. Like you would think, well, yeah, that's not a pin joint.
It doesn't have to be able to swivel.
Right.
It just has to be.
That's right.
Okay.
But that'll give you good calculations, and you could do the calculations assuming that the orientations were fixed like that, but it would just be a lot more time consuming, and in the end give you the same information. Any other questions? Yeah.
These equations, are they statics?
Yes.
So that after like course, is statics one course?
One. Yep. So you can take that after physics 1.
So after that, we kind of calculate all sorts of pressures, like human body parts to bridges.
Mm-hmm. Yeah, I mean, sometimes I think it's a little tricky to figure out how to apply, but yeah, I remember thinking statics is just really cool because you get to the point where you can, like, you go outside and you just see all these things you could apply it to, you know. I like statics as a class because the way it occurs to me, it's like maybe the one class you have where you don't learn any new science, you know, like
all you're doing is just getting a million repetitions of like applying things that you already learned in physics 1, you know. It's sort of like a semester of stretching out and just like solidifying stuff. And yeah, right. I like that.
Anything else?
Okay, well, thanks.
Yeah, thank you.
Yeah, sure.
That's super awesome.
Yeah, sure.